Last week we looked at 4 new terms that we hadn't seen before. First one being electric potential energy, then we had electric potential energy difference, then electric potential, then electric potential difference. 4 terms that mean different things, 4 terms that look almost exactly the same. Electric potential energy, that first term, is the energy stored in a system of 2 charges a certain distance apart. When we put 2 charges a certain distance apart, there will be a force of attraction or a force of repulsion. There will therefore be a certain amount of potential energy. Whenever we have that force, we're going to have potential energy. The energy stored in that system of those 2 charges is the electric potential energy. The symbol for electric potential energy? Just simply EP. What would the units for electric potential energy be? What would the usual units be, the normal units be for electric potential energy? It's not hard. What's the units for any kind of energy? Joules, yeah, it's joules. It's no different for electric potential energy. It's going to be joules. Now, every once in a while, we may use electron volts. We know how to convert joules to electron volts and electron volts to joules, right? And we'll do that in a few minutes here just as a practice. Most times joules, sometimes electron volts. Electric potential energy difference, I think this is a pretty straightforward one, right? Electric potential energy difference is literally the difference between electric potential energy in one situation versus another. So you got a certain amount of potential energy here, you got a certain amount of potential energy here. The difference between the two is the electric potential energy difference. What would the symbol for that be? This one's not hard either. Not the units, but the symbol. If potential energy is EP, then potential energy difference would be delta EP. What else can we call electric potential energy difference? What's another word that we can use that describes the exact same thing? Work. And the symbol for that is W. And of course, we can also find work by multiplying force times the displacement. When you're writing that out, make sure you put the arrow sign over the delta D, reminding you that it's the displacement of the charge, how far the charge has moved versus the distance between the plates, there, which is a scalar. What would the units for change in potential be, or the units for work? If the units for energy are joules, then the units for change in energy are going to be joules, or electron volts, depending upon the scenario. Now electric potential. This one's a little bit confusing. Words almost exactly the same, or the terms almost exactly the same as the first one, but the meaning is a little bit different. Potential energy is the energy stored in the system. Potential is the energy stored per unit charge, per coulomb of charge. We have 9 people in this room. We have $180 total. The equivalent, or the analog here, 180 joules of energy, total energy. But all of a sudden, if we want to find the amount of energy per person, or the money per person, then we would say 180 divided by 9 is 20. So 20 would be the money per person. 20 is the analog to the energy per charge. 20 is the analog to the electric potential. To find the electric potential, given by the symbol capital V, by the way, we're simply going to divide the total amount of energy divided by the amount of charge that we have. That gives us the amount of energy per charge. By the way, that's a capital V. Sometimes I write these little squiggly things on the top of that V to remind us that it's not a lowercase v, it's not speed. What would the units for electric potential be from that equation? What do you get from that equation? Joules per coulomb, good. And another set of units that we can use that describes the same thing as a joule per coulomb does is the volt, good. Potential difference. Potential difference is going to be delta capital V. And you can find that by saying it's VF minus VI, the final potential minus the initial potential. But you could also say if potential is E over Q, the potential difference would be delta E over Q. So you can find it in 2 ways, VF minus VI or delta E over Q. The units for that would be joules per coulomb or volts. Finally, last week, on Thursday, we took a look at conservation of energy. We said that anytime a charge speeds up or slows down, that's what we're going to do, conservation of energy. But We're going to simplify it a little bit, at least in the way we think of it, by picturing it as a car either going up a hill or down the hill. What happens to the speed of a car as it goes up the hill? It slows down. What happens to the speed of the car as it goes down the hill? It speeds up. So whenever we have a charged particle speeding up, we're going to picture it as the car going down the hill. We're going to visualize the car accelerating down the hill. Whenever we have a charged particle that's slowing down, we're going to picture it as, or visualize it as, the car going up the hill with the conversion of kinetic to potential energy. When that car is going down the hill, of course, we can describe it by EI is equal to EF. What kind of energy does it have at the top of the hill? What kind does it always have at the top of the hill? It's got to have potential. What kind does it sometimes have at the top of the hill? Right. Now, we're going to assume in this case that it's at rest at the top of the hill, therefore it has just potential. It has to have potential. It may also have kinetic that we have to add in there, maybe not. At the end of the problem, or at the bottom of the hill, what kind of energy, Christine, does it have? Right. Now, it may also have potential if we're trying to find the speed part way down the hill, but it's going to have kinetic for sure. Now, when we're solving a problem where the charged particle is speeding up, we're just going to replace that mgh with QV. We're just going to replace the gravitational potential energy with the electric potential energy. Now, when the car is going up the hill, we'll describe it in basically the same way, EI is equal to EF. But this time, at the bottom of the hill, Jordan, it would have what kind of energy? If the car is at the bottom of the hill going up the hill, what kind of energy does the car have at the bottom? Right. When the car reaches the top of the hill, what kind of energy does it have? Potential, right. Now, it may also have kinetic energy at the top of the hill. It depends upon if it's still moving or not, but it's going to have potential for sure. We're going to replace that mgh with QV. So instead of being gravitational potential energy, it's going to be electric potential energy. Plug in your numbers, solve for what you need to find. We were given 2 questions for homework on page 571. I had a request to go over both of those questions. Okay, let's do that now then. Number 1 says a negative charge of 3 times 10 to the negative 9 coulombs is at rest at a position in the electric field of a larger positive charge and has this much potential energy. When it's released, the negative charge accelerates toward the positive charge. What's the kinetic energy of the negative charge just before it reaches, or just before it strikes the larger positive charge? Lots of words in here and lots of things that can seemingly make this difficult, but don't let it. Okay, don't let those words win. Okay, beat those words. In the end here, we have a charged particle that is speeding up. That's like a car that's doing what? When does a car speed up? Going down the hill. So let's treat this as a problem with a car going down the hill. And then we'll modify it to suit the electric charge when we need to. EI is equal to EF. When the charged particle is at rest when the car is at rest at the top of the hill, what kind of energy does it have, Jared? What kind does it have at the top of the hill at rest? Right. So let's write in mgh here. It's at rest, so there's no kinetic. When it reaches the bottom of the hill, what kind of energy does the car have? Kinetic energy, 1f squared. Now, see what I've done there? All I've done is pictured the car at the top of the hill, the bottom of the hill, what kind of energy does it have? And then I've subbed in equations. I'm going to replace mgh with qv, because of course we're not really talking about gravity here, we're talking about electricity. Otherwise, the equation is the same. They gave me a bit of a break in this question. I don't actually need to sub in those equations per se, because we're told what the value of QV is. We don't need to write in QV. If we know that Q times V already is 3.2 times 10 to the negative 12 joules. Similarly, if we're just looking for the value of EK, and we know that EK is equal to potential energy, and we know the value of the potential energy, don't we already know the value of EK? the final kinetic energy is going to be 3.2 times 10 to the negative 12 joules. Does that make sense? We could plug in numbers if we had them for Q and V and M and VF and whatever, but we don't need to here. We've got the initial potential energy. That will be equal to the final kinetic energy. So EK is simply going to be 3.2 times 10 to the minus 17, 10 to the minus 12. Good? Let's take a look at question 2 here. There's a small sphere with a charge of negative 2 microcoulombs and a mass of 1.7 times 10 to the minus 3. Accelerates from rest toward a larger positive charge again. If the speed of the sphere just before it strikes is 5.2 times 10 to the 4, how much potential energy did the negative charge lose? Charged particles speeding up or slowing down? Speeding up. Every time we see a charged particle speeding up, we want to do EI equals EF. We want to picture it as the car going down the hill. What kind of energy does the car have at the top of the hill? Potential. What kind of energy does the car have at the bottom of the hill, Krissa? Good. Now we're going to replace MGH with QV. Now you don't even have to write in the MGH if you don't want to. Bless you. We're just writing the MGH so that we can draw that analogy between gravity and electricity. Okay? If you can do that analogy kind of in your head without writing in the MGH, just putting in QV right off the top, then that's fine too. Okay, we've got the charge here. It's 2.00 times 10 to the minus 6. Oh, something I missed. Should have circled that as well, right? To remind me that it's non-standard. VI, don't know that. You know what, let's erase this actually. This is correct. What I have written down is absolutely correct. But look, if I have the mass and I have the final speed and I want to find how much potential energy it lost, let's not even write this in. Let's just leave it as EP initial. That's going to give me the initial potential energy. If I end up with 0 potential energy, well then how much did I lose? What did I start with? If I started with 10, I end up with 0, then I lost 10. So let's get the initial potential energy. Let's get the initial potential energy not by multiplying Q times V. Let's get the initial potential energy by multiplying 1/2 mv squared, getting the final kinetic, and then setting the final kinetic equal to the initial potential. When we do the math on that one, I think it works out to be 2.30 times 10 to the 6. Is that okay? When I'm doing these problems, I always start off by writing the equations. QV, 1/2 mv squared, I always do that. Even if in the end, I don't need to. Like in both of these questions, I didn't need QV or 1/2 mv squared. Or at least in the first question. Second question, I didn't need QV. But I wrote them in because that's what I do. If I discover that I don't need them, then I just scratch them out or I replace them with EP or EK or whatever the relevant thing is. If you need them, it's there. If not, then scratch them out. Let's take a look at another one here, okay? This is a 572. Last example that we're going to do today. 2 vertical plates. The fact that they're vertical doesn't really matter. They're connected to a DC power supply as shown in the diagram. The electric potential between the plates is 2.0 times 10 to the 3 volts. That really should say potential difference. You can't have a potential between 2 plates. You can have a potential at one plate and the other, but the potential between 2 plates would be the difference in potential, or the potential difference. Although it's probably not going to really throw you off in this question. We got a mass here of 3 times 10 to the negative 15 kilograms, a positive charge. It accelerates toward the negative plate. We want to find the speed as it reaches the other one. Forget about the diagram for a second. If it helps you, I mean, I guess don't forget about it, but don't ignore it. But I don't know that we need it here. What's happening to this charge here? What's happening to this charged particle? Speeding up, slowing down? What is it? Michael? It's speeding up. If it's speeding up, that's like a car doing what? Natalie? Right. If a car is going down a hill, we're going to set it up as EI is equal to EF with potential energy at the top and kinetic energy at the bottom. But we're going to replace MGH with QV. So instead of being gravity potential, it's electric potential. Now we're going to sub in our numbers. Q is 2.6 times 10 to the minus 12. V initial is 2.0 times 10 to the 3. Now, technically, we're not given the initial potential. We're given the potential difference. But if the final potential is 0, then the change in potential is going to be equal to whatever the initial is. We're given the change. The initial must be the same value, 2.0 times 10 to the 3. The mass is 3 times 10 to the negative 15. And we're going to multiply that by VF squared. Let's pull this up on our calculator and do this. Let's say 2.6 times 10 to the minus 12 times by 2,000. Let's multiply that by 2 to get rid of the half. Let's divide that by 3 times 10 to the negative 15. And then let's finally square root that. We get 1.9 times 10 to the 3. That okay? In some ways, that's probably easier than the questions we did for homework. It's more work, but you don't have to recognize the values that you were given for energy, how they can be plugged in there. Okay, although it's more work here, sometimes people find these questions a little bit easier than the questions we had last night. You are going to do 3 things here today. The first thing is the practice problems that go along with this on page 572. There's 2 of them. Then we're going to work on a few multiple choice questions. And then you're going to have an opportunity to work on worksheet number 9, which is what finishes off the unit for us. Okay. We are done in terms of new stuff. We're just going to practice this whole conservation of energy thing today with those 2 questions that go with this, with those multiple choice questions, and with that worksheet. Okay, right now, let's take a look at those 2 questions that go along with this. 572, we'll give you about 5 minutes, and then we'll take a look at those ones. Take a look at number 2 here, everyone. It says if a charge of negative 6.0 times 10 to the minus 6 coulombs gains this much kinetic energy as it accelerates between 2 oppositely charged plates, what is the potential difference between the 2 parallel plates? Hey, if this charge of negative 6 times 10 to the minus 6 coulombs is accelerating, is speeding up, that's like a car doing what? Up the hill, down the hill? Down the hill, good. If it's a car going down the hill, then we're going to say, of course, EI is equal to EF. But specifically, we're going to say that the initial energy is potential. It starts off at rest. We'll assume that it starts at rest, at least. Okay, it ends off moving, so it's going to have kinetic energy. Potential ends up being converted to kinetic energy. Now, we're looking for the potential energy, the potential difference between the 2. So let's replace MGH, the gravitational potential energy, with electric potential. The charge is 6.0 times 10 to the minus 6 times VI is equal to, once again, we've got that situation where we have the number already. If it gains this much kinetic energy, then this must be the kinetic energy that it has at the end of the problem. So let's just replace 1 FmV squared with a number, 3.2 times 10 to the minus 4. When we do the math here, we end up getting 53.3 volts. Now, some of you might look at this and say, well, how do we know it started at rest? How do we know that it wasn't moving? Let's assume that it didn't start at rest for a second. Okay, let's assume that it started with a certain speed that gave it a certain kinetic energy. A kinetic energy, let's say, right off the top of 1 times 10 to the negative 4 joules. Well, then the question would look like this. Right? The potential energy on the left side plus the kinetic energy on the left side equals what kinetic energy would we have on the right side? Well, if we gained 3.2 times 10 to the minus 4 and we started off with 1 times 10 to the minus 4, we'd now have 4.2 times 10 to the minus 4. Solve for VI. What are you going to get? Exactly the same thing as we did just get, 53.3 volts. So what we're saying here is that because we've got the change in kinetic energy, we assumed that it was the final value of kinetic energy and that the initial value was 0. It doesn't matter what we assume the initial value of the kinetic energy is, as long as our final kinetic energy reflects that based on the change in kinetic energy that we have. Does that make sense? Christina? The negative charge, you mean? We never include the negative charge because for us, a negative means direction. A negative charge, I mean, that's important for some reasons, like determining whether something's attractive or repulsive, but we're never going to include a negative charge in the equation because for equations for us, we don't want to mix and match two different sign conventions. For us, the sign convention that we use, positive means to the right, negative means... Right, never include it in the equation, never. Not pretty much, but never include it in the equation. Okay? All right, I'd like to take a look at a couple multiple choice questions here, 4 of them actually. A couple groups of 2. 56 through 59. I want to do 56 and 57 first. They're the ones that are directly related to what we've just been doing on Thursday before the break and today. Read through this information. Take a look at the questions that are in your worksheet booklet at the end of it, 56, 57. See what you can do with them. I'll tell you right now, they will seem challenging. But I'll also tell you right now that the questions themselves are, for the most part, pretty easy. It's sifting through the information. Yeah, that's more the exercise that I want to do here right now, is sift through the information. See what you can do. We'll give you about 5 minutes to do those first 2 questions, and then we'll take a look at those, and we'll give you a few more minutes to do the last 2 questions. Let's take a look at this, everyone. First, we'll read through it, and we'll just make little notes if we see something that kind of jumps out at us. If there happens to be anything that leads us to a silly mistake, then we'll circle that or underline it or highlight it or whatever. We'll try to get what we can out of this information as we're reading through it, though, okay? Deep Space 1 mission, DS-1 uses an ion propulsion system, the IPS, on the DS-1 capsule. The IPS involves ionizing atoms of xenon, accelerating them through an electric field, and stop right there. Accelerating them through an electric field. Ions of xenon, they're charged particles. If they're accelerating, then they're speeding up. When charged particles speed up, it's like a car going down the hill, and we can treat that as a conservation of energy problem. Now, I'm not going to solve anything yet because I have no data yet. But if that jumps out at me as I'm reading through it, then make a note about it. When you go to actually solve the question after spending 5 minutes of reading through this, you may forget way back in the beginning that you saw EI is equal to EF. Okay, write it down. Okay, let's keep going. Ejecting the ions into space behind the capsule. Then we get the diagram. It says in the IPS chamber, the high-speed electrons collide with the xenon atoms. These collisions can ionize the xenon atoms. I see this word collision, and as odd as this might seem right now, the whole idea of conservation of momentum actually kind of jumps out at me there. Now, it seems really odd that we're doing an electricity unit with conservation of energy in the context of electricity, but yet this whole idea of conservation of momentum jumped out at me. Okay, when I see this question right now, I think, look, I'm probably not going to use conservation of momentum, but I'm going to write it down because I spotted that. I spotted there's a collision, and I spotted that I can use conservation of momentum if it helps me. So I'll write it down, okay? The electric fields then accelerate the ions and ejects them from the IPS chamber. This propels the DS1 capsule forward. Then we have a bunch of information here, a bunch of data. The propellant ions says Xe plus. That's giving us the charge of the xenon. What is the charge of the xenon ion based on that notation there? If I said Cl2 minus, then the charge of that chlorine ion would be negative 2 times 1.6 times 10 to the minus 19. This one's going to be positive 1 times 1.6 times 10 to the minus 19. So we've got the charge of the xenon. Got a whole bunch of other stuff as well. I see a strange unit there, electron volts, and I see kilometers per second there, which is an even stranger unit. Now we got to do our thing. Read the question, see what we're being asked. The minimum electron speed necessary to ionize the xenon atoms is what? I don't know about you guys, but the first thing that came to my mind when I saw this was EI equals EF, conservation of energy. Right? That's what I wrote down. I wrote down that that was a valid concept. I'm seeing this whole accelerate xenon ions, xenon atoms. I'm thinking conservation of energy. We start off with potential. We end off with kinetic. Got charge, I've got mass. I don't have the speed, nor do I have the initial potential. So that doesn't work for me. It's a valid concept, but I have two unknowns. That's okay. Let's go back to basic principles here. We want to find the speed of the electron necessary to ionize a xenon atom. Go back to this data here. The energy required to ionize a xenon atom is this. The speed required? Well, if we've got the kinetic energy, how do we find speed? Remember what I said when you were doing this the first time? I said, don't make this harder than it has to be. If a car has 10,000 joules of kinetic energy at a mass of 2,000 kilograms, what's its speed? How'd you find that? The question was, if a car has 10,000 joules of kinetic energy and a mass of 2,000 kilograms, how do I find the speed of that car? Christine, how do I find the speed of that car? Set kinetic energy of the car equal to 1/2 mv squared, solve for v, right? The question here is, what's the speed of the electron necessary to ionize a xenon atom? We have the kinetic energy of the electron necessary to ionize a xenon atom right here. If we have the kinetic energy of the electron and we have the mass of the electron, then we can find the speed of the electron just like we did the speed of the car. We're going to say not this, but rather we're going to say Ek is equal to 1/2 mv squared. V is equal to 2 Ek over m. Kinetic energy is given to us on that sheet. The mass is given to us on our data sheet. We just have to convert the kinetic energy from 12.1 electron volts to joules. And we're going to do that by saying 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. 12.1 electron volts is equal to x joules. Get that number, plug it into there, solve for speed. When we do, it works out to be 2.06 times 10 to the 6 meters per second. It's the only one that could be the correct answer because it's the only one that has a speed that's less than the speed of light, 3 times 10 to the 8 meters per second. So we're not suggesting that that whole EI equals EF is not valid. It is valid. It just didn't help us. Don't be afraid to try it. Okay, I tried it. I tried EI equals EF the first time I did this question. It didn't work because we had too many unknowns. But it didn't get me the wrong answer. As long as I'm trying something that's valid, we don't ever need to be afraid to try it. Worst case scenario is it doesn't give me the answer and I try something else. It's usually pretty simple. This one was Ek is equal to 1/2 mv squared. Don't overlook the obvious. Now, question 57, where we're asked to find the potential difference necessary to accelerate the xenon ion. This is where we're going to do what I thought we were going to do in 56. This is where we're going to say it's like a car going down the hill. We start off with potential energy at the top of the hill. We end up with kinetic energy at the bottom of the hill. So mgh becomes qv, and I sub in my numbers to solve for vi. The charge of the electron is 1.6 times 10 to the minus 19. The mass of the electron, sorry, is it an electron that I'm doing here? Jared, what is it? It's a xenon ion, right? Xenon ion, the charge is 1.6 times 10 to the minus 19, but the mass is on that sheet, right, in the box of information that we had there. And the final speed, I believe that was 43,000 meters per second, 43 kilometers per second, or 43,000 meters per second. We end up solving for VI. When we do, we get 1.26 times 10 to the 3 volts. Now, we're actually looking for the potential difference. We didn't find that. We found the initial potential. But if the initial potential is 1,260 and the final potential is 0, then it's the same as the potential difference. The initial potential will be the same as whatever the difference was. Look at what's up on the board right now. This seemed hard to us. Why? Because the people that made up this question tried to make it hard for you. We just have to be always confident that we know the concept. Right? The two concepts here, EK is equal to 1 FFE squared, EI is equal to EF, they're not hard. We just got to recognize that that's what it is that we do. Okay, if we can get past that, then we should be in great shape. I'll give you just a couple of minutes to see if you can at least get an idea for question 58 here. If you can't solve it, that's okay. Just see if you can get an idea for it, and then we'll take a look at it in about 2 minutes. All right, if all of the xenon propellant could be expelled in a single short burst, the change in speed of the DS1 capsule after the fuel had been burned or exhausted would be what? Anybody have an idea for this? Don't be afraid to try something. Don't be afraid to just blurt something out, okay? If you're wrong, so what? It's better than the other 7 people in the room that are blurting out nothing. Is this not the same thing as firing a gun? They fire a gun, the bullet goes one way, the gun goes the other way. When this propellant goes out the back of the capsule goes, the propellant goes one way, the capsule goes the other way. Is that not the same thing? How did we analyze the firing of a gun? Sorry? Yeah, that was a conservation of momentum problem, right? PI equals PF. Let's do that here. The initial momentum is equal to the final momentum. The initial is 0 because it starts at rest. The final momentum is m1 v1f plus m2 v2f. M1, you got to be careful here. We're talking about the mass of the xenon propellant, not the mass of a single xenon ion, but the mass of the xenon propellant, which is 81.5 kilograms. It gets expelled at, what was it, 43,000 meters per second? Yeah, 43,000 meters per second. The mass of the capsule is 489.5 kilograms. And we're going to solve for V2F. When we solve for V2F, I think we end up getting D, 7.16 times 10 to the 3. Anybody have that? What principle did we use that best describes the propulsion of this DS1 capsule? Conservation of momentum, right? If you look ahead there at 59, that can give you a bit of a hint as to what to do with 58, right? So you're not sure what to do with it. Move on, go to the next question. You read 59 and all of a sudden, wait a second, momentum's in there. I never thought of momentum, haven't done momentum in a while. Go back and try it. You will not get a conservation of momentum question on Wednesday's test. I won't do that to you. Okay, but we went through this question today mainly because it went with the other two questions. It fit well. Questions 56 and 57. But also because we have to be prepared for that. We have to be prepared for scenarios by the end of the year where we're mixing and matching units. Unit 1, Unit 2, Unit 3, Unit 4, all in the same scenario. Okay. Don't think just because this is the last thing we've done, conservation of energy, that it's the only thing that can relate to a question. All right, your assignment is due tomorrow. What I'd like you to do right now for the last 10 minutes or so is to work on worksheet number 9, please. Worksheet number 9.